Okay, hello, upper six. I'm back. This worksheet, or this tutorial rather, deals with proof by mathematical induction. Um, for the most part, I know you know the procedure required to go through and prove an expression by mathematical induction. I have a list of 10 problems here. The first three are based on the proofs that you've done in the lower in the unit one in the lower six. If you were to go back to your unit one notes, you will see if not these first three problems, if not exactly the same, very similar ones. The first one deals with generic summation. The next one deals with an inequality. The third one is divisibility. Those were the three types you had in the unit one. But I put these three back so that it'll give you a good review. The next several, well, the fourth one is the Morse theorem, which I will work on. The next several, 5, 6, 7, 8, I think, yes, they deal with proof by induction based on the use of sequences. Those come mostly, not exclusively, but mostly I see those in the unit 2. Proof by induction in the unit 2 pure math involve the use of sequences. So you'll get reasonably decent practice on that. And then the last two, one is on differentiation, and the last one is on the binomial theorem. As you see, I have a note in red there. This one is difficult. They want the proof by induction using the binomial theorem, or proving the binomial theorem by mathematical induction. It's not that easy. All right, so let me do not the first two, like I said. I'll do the Morse theorem, and I'll do number 5, which is one with a sequence. And we'll see how those go. So let's run it. Prove by mathematical induction that cos theta plus I sine theta to the power n is equal to cos n theta plus I sine n theta. That is the Morse theorem as you learned it when we did complex numbers. For all values of n which are members of the set of natural numbers. Now we're going to go through the procedure exactly. The procedure did not change. Concepts don't change. Well, the concept didn't change in terms of how you go through proof by induction, and as also the procedure didn't change. So you're going to prove the thing they're asking you to prove. You call it your PN statement. Cos theta plus I sine theta to the power n equal cos n theta plus I sine n theta. This guy is your P sub n statement. And we're going to first prove that Pn is true for n equal 1, starting value. Then for n equal 1, continue doing it exactly the way I've been doing it. If you take the left-hand side, which is cos theta plus I sine theta, all to the power n, n being 1 gives me cos theta plus I sine theta to the power 1, which is just cos theta plus I sine theta. Right-hand side gives me cos n theta plus I sine n theta. And of course, if you put n equal 1 there, you also get cos 1 theta or cos theta plus I sine 1 theta or I sine theta. What does this tell us? This implies that P1 is true. Remember the next step? Assume we're in trouble with this thing still. Don't know exactly why. Assume that Pn is true for n equal k. The expression now becomes cos theta plus I sine theta to the power k is equal to cos k theta plus I sine k theta. And this is your pk statement, which you assume to be correct. And then based on the assumption, that pk is true, we'll prove that p sub k plus 1 is true. That is, we will prove that cos theta plus I sine theta to the power k plus 1 is equal to cos of k plus 1 theta plus I sine of k plus 1 theta. The fact that you said that you're going to prove that, that's not the proof. How do we go about proving that? Well, what we'll do, we have to break down this left-hand side into two parts. One part which will look like the pk statement so that we can plug in that assumption from the pk statement. So we'll rewrite cos theta plus I sine theta to the k plus 1 is equal to cos theta plus I sine theta to the power k times cos theta plus I sine theta. That is basic indices right there. Cos theta plus I sine theta to the k plus 1 is equal to, and now we're going to plug in the expression for cos theta plus I sine theta to the k from the pk statement. We're going to plug in this. According to the pk statement, cos theta plus I sine theta to the k is cos k theta plus I sine k theta. So we're going to plug in, and this becomes cos k theta plus I sine k theta times cos theta plus I sine theta. So we got a little multiplication there to do. Cos theta plus I sine theta to the power k plus 1 is equal to cos k theta times cos theta plus cos k theta times I sine theta plus I sine k theta times cos theta plus I squared times sine k theta times sine theta. Cos theta plus I sine theta to the power k plus 1. Gotta watch your handwriting there, sir. is equal to, okay, we'll pull all the real parts together. So this becomes cos k theta cos theta. I squared we know is minus 1, so that would be minus sine k theta sine theta. The two parts with the I in front, we'll rewrite those parts as I into I'll write the one with the sign first. There. I into sine k theta cos theta. Sine k theta cos theta plus cos k theta sine theta. And everybody should recognize their compound angle identities there. Cos A cos B minus sine A sine B is cos of A plus B. And sine A cos B plus cos A sine B. Let me say that again. Cos A cos B minus sine A sine B is cos of A plus B. And sine A cos B plus cos A sine B is sine of A plus B. A in this case, of course, is k theta and B is theta. So therefore, using the compound angle identities, I will get cos theta plus I sine theta all to the power k plus 1 is equal to cos of k theta plus theta. That's the cos of A plus B. And then plus I sine of k theta plus theta. From both brackets, we can factor out theta. And we get cos theta plus I sine theta to the power k plus 1 is equal to cos of k plus 1 all times theta plus I sine of k plus 1 theta. Right? And we've gotten what we're supposed to get. If it's true for k, it must be true for k plus 1, because k plus 1 replaces k everywhere in the pk statement. So we can write a nice little statement here that says what we've just proven is if pk is true, then pk plus 1 is true. And then the last part of the proof is the conclusion. The conclusion says, but P1 is true, which would imply that P2 is true. You just established the link between PK and PK plus 1. We said that if PK is true, then PK plus 1 is true. So if P1 is true, then the very next one must be true. And we know that P1 is true because we proved it at the beginning. But P1 is true, which implies that P2 is true, which would imply that P3 is true. And so on, ellipses, which implies that Pn is true. For all values of n, which are members of the set of natural numbers. And that's that. That's not too bad. So the four main steps. You prove that the expression is true for 1. Right there. Let me separate them. The next step is you make the assumption that the statement is true for n equal k. That's an entire step. Wow. And based on the assumption pk is true, we'll prove that pk plus 1 is true. That is, we'll prove this expression. So we went through the entire process until we actually proved it right there. All right, isn't that what we said? Yes, cos theta plus I sin theta k plus 1. It's cos k plus 1 theta plus I sin k plus 1 theta. That's step 3, which ends there. And then the last step is the conclusion, which means if P1 is, which is saying if P1 is true, that implies that P2 is true, which implies that P3 is true, which implies that P4 is true, and so on and so on and so on, until you basically have exhausted all the natural numbers. Okay, the second one that I want to work on, by the way, both of these came from the worksheet, so you have 2 less to do, but just make sure you understand how to do these. You can probably do them on your own first and then check back. The only ones, well, I haven't done with you really, though the entire concept is the same, are the ones with sequences, which is, I'm about to do one right here. Okay, it says given that u sub n plus 2 is equal to 5 times u sub n plus 1 minus 6 times u sub n, where u sub 1 is 1 and u sub 2 is 5, prove by mathematical induction that u sub n is equal to 3 to the n minus 2 to the n. And of course it's for the usual, for all values of n which are members of the set of natural numbers. All right. The thing that they want you to prove, that's what you're going to call your P sub n statement. And the thing that they want me to prove is that u sub n is equal to 3 to the n minus 2 to the n. Right there. This is my P sub n statement. Now, if you think about this logically, you were given a recurrence relation at the beginning, u sub n plus 2, which depended upon 2 previous values. That's important, the fact that it depended on 2 previous values. U sub n plus 2 depended upon u sub n plus 1, and it also depended upon u sub n. That's why you were given 2 initial values. You were given u1 and u2, because that's the only way you'll find the next value in that sequence. Now, what they're asking you to show basically is that you can replace that recurrence relation with a non-recurrence relation that will give you the same set of values. And they're asking you to prove that that non-recurrence relationship is correct. And you got to prove it by induction, which is pretty cool. And you'd remember the fundamental difference between recurrence and non-recurrence relations. The recurrence relations, you need at least 1 previous term. In this case, you need exactly 2 previous terms to get the next one. In a non-recurrence relation, you don't need any previous term to get the next term. You just jump right to the term that you need, and you're good to go. So effectively, they're asking us to prove that this non-recurrence relation, which we establish as our PN statement, that you can get the terms of the sequence from that. Excuse me. Let's sip of water. Okay. All right, well, let's proceed as before. Now, remember, I just discussed that the fact that 2 previous terms were required to get the next term means that you have to prove 2 initial values. You have to prove that P1 is true, and you have to prove that P2 is true. This is one of the cases in which you definitely need two previous terms to prove the next term. All right, how do we do it? So let's start with n equal 1. For n equal 1, u sub 1, well, let's do it exactly as we've been doing it before. Give me a second here. For n equal 1, for the left-hand side, for the left-hand side, u sub n would be equal to u sub 1. But u sub 1 was given as 1. That was given to us. It's right there. u1 equal 1. Right there. That was given. You take the right-hand side, which is 3 to the n minus 2 to the n, and we're going to plug 1 into that. So that's 3 to the 1 minus 2 to the 1, and everybody can see that that's 1. What this means? This means that P1 is true. This implies that P1 is true. We also have to prove P2, folks, because P2 is also given. And again, I repeat, you needed two previous terms to get the next term in the sequence using the recurrence relation. So for n equal 2, left-hand side is un, which becomes u2. But u2 is also given. That was given as 5. That was given to us. From the right-hand side of the expression, we calculate 3 to the n minus 2 to the n, which is, with n equal to 3 to the 2 minus 2 to the 2. 9 minus 4, which is also 5. Voila. What's my conclusion here? This implies that P2 is also true. So what do we do next? That's the end of the first step. Step 2, we will assume that Pn is true for n equal k and n equal k plus 1. Gotta make two assumptions here as well. You always needed two things to prove the next one. So let's plug in n equal k. We'll get u sub k is equal to 3 to the k minus 2 to the k. This is my pk statement. And the next one is u sub k plus 1 is equal to 3 to the power k plus 1 minus 2 to the power k plus 1. And this is my p sub k plus 1 statement. You needed those two so you can prove the next one. Okay. Based on this, so that's step 2. Step 3. Based on the assumptions that pk and pk plus 1 are true, we will prove that p sub k plus 2 is true. That is, we will prove that u sub k plus 2 is equal to 3 to the power k plus 2 minus 2 to the power k plus 2. Now we can prove that, buddy. Put myself in a lock here. All right, let's see how we're going to do that. Now remember, you were given a recurrence relation. We're going to use that to our advantage. You can use that to prove it. Let me write back the recurrence relation. U sub n plus 2 5 minus 6 is equal to 5 times u sub n plus 1 minus 6 times u sub n. Right? This is from the recurrence relation given. That's the case. Now, I'm allowed to put any value of n that I want into that recurrence relation. I can put n equal 3, I can put n equal 5. I can put whatever I want. But I will always need 2 previous values to get the next one. Now, I'm choosing to plug in n equal k into that recurrence relation. We will substitute n equal k into the above recurrence relation. And that will give us u sub k plus 2 is equal to 5 times u sub k plus 1 minus 6 times u sub k. So, from our p sub n statement and our p sub n plus 1 statement, p sub k statement and p sub k plus 1 statement, we'll simply plug those in. U sub k up there is 3 to the k minus 2 to the k, and u sub k plus 1 is 3 to the k plus 1 minus 2 to the k plus 1. So let's plug them in. U sub k plus 2 is equal to 5 times the expression for u sub k plus 1, which is 3 to the power k plus 1 minus 2 to the power k plus 1 minus 6 times the expression for u sub k, which is 3 to the k minus 2 to the k, like so. Opening up our brackets and thing, I will get, give myself some space here. Yes, if we open up those brackets, I'll get u sub k plus 2 is equal to 5 times 3 to the power k plus 1 minus 5 times 2 to the power k plus 1. Then this is minus 6 times 3 to the power k plus 6 times 2 to the power k. I need to make it look like that. U sub k plus 2 must end up being this. 3 to the k plus 2 minus 2 to the k plus 2. So let me see if I can pull the parts with 3 to a power together. What I'm going to do, I'm going to strip a power of 1 from the 3 to the k plus 1. This looks like u sub k plus 2 is equal to 5 times 3 times 3 to the k. That makes sense? Stripped off 3 to the power 1 from that. I'll pull next to that minus 6 times 3 to the k. That's that term right there. So I pull these two terms next to each other. And then the terms with 2 to the k I'll pull next to each other. I'll write this one first. Plus 6 times 2 to the k. And then minus 5 times 2 times 2 to the k, like that. U sub k plus 2 is equal to 5 3's 15 times 3 to the k minus 6 times 3 to the k plus, this becomes 6 times 2 to the k minus 10 times 2 to the k. Okay, everybody knows 15 apples minus 6 apples is 9 apples. U sub k plus 2 will give me 9 times 3 to the k plus 6 minus 10 would give me minus 4. So this would be minus 4 times 2 to the k. I can rewrite 9 as 3 squared times 3 to the k, and I can rewrite 4 as 2 squared times 2 to the k. Voila. U sub k plus 2 is equal to, using my indices again, 3 to the k plus 2 minus 2 to the k plus 2, which is the thing I said I was going to prove right there, right up there. Okay, so at this point I can say that if pk and pk plus 1 are true, that implies that the next one is true. P sub k plus 2 is true. Remember, all throughout this problem, you needed 2 previous things to prove the next one. You needed pk and pk plus 1 to prove pk plus 2. In your introduction, you needed p1 and p2. You needed to prove both of them. That's why they gave you those 2 values to begin with. And for the original recurrence relation, you always need 2 previous values to get the next one. All right, what would my conclusion look like? Interesting way in which I'm going to write this out. For the conclusion, it should be written something like this. But P1 and P2 are true, which implies that P3 is true. And P2 and P3 are true, which implies that P4 is true. I'll do one more. And we can say that P3 and P4 are true, which implies that P5 is true. You always need 2 previous ones to be true for the next one to be true. Yada, yada, yada. Which implies that Pn is true for all values of n, which are members of the set of natural numbers. Like so. And that's the end of that proof. Okay, so you have 2 nice problems done there. You will go through the rest in the worksheet. Somewhat challenging, but that's why you study math. To overcome the challenges and show that you're just as good as everybody else. Okay. I'm going to stop this worksheet right here. I'll stop this tutorial right here. And then, like I said, y'all can have fun with the rest of the problems.